Okay, so today we are introducing constrained optimization. So basically, we can now solve optimization problems with constraint functions after today's lecture. And the method I'm going to introduce today is called linear programming. LP. Okay, so if we have a constraint optimization problem, what's the general format? Let's take a look at a general problem. So basically, minimizing f of x, we can have multiple x. Subject to, we can have gi x smaller than 0, where I goes from 1 to, for example, n, which means I may have n inequality constraints. Okay, and I could have h, for example, I have an index of j, and they must equals to 0, where I can have j goes from 1 to, for example, m. I can have m equality constraints. Okay, so in general, I can have constraint optimization formulation in this way. Okay. For linear programming, we can only handle equality constraints. Since linear programming can only handle equality constraints, how do we deal with those inequality constraints? So we have to introduce something called slack variables or surplus variables. I will let you know what those are in order to transform inequality constraints to equality ones. So let's have one example. Let's say, so now I'm going to introduce something called slack variable. In some particular problem where I have 3x1 plus 2x2 smaller than 3, I can transform this equation into equality constraint by adding one more variable to this equation. How do we do it? We can do this. We can add one additional variable, so-called a slack variable, on the left-hand side of the equation, and we need to make sure S1 is greater than 0 or equals to 0. In this case, let's take a look at the scenario of S1 equals to 0. When S1 equals to 0, we have 3x1 plus 2x2 equals to 3. When S1 is positive, we are sure 3x1 plus 2x2 is smaller than 3. Right? So by adding this slack variable, I can rewrite inequality constraint to a new format. And this new format is in the equality form. So by doing so, I can transform inequality constraint to equality constraint. Why do we do that? Because linear programming can only handle equality constraints. Okay. So this is called the slack variable. There's another situation where we need to use so-called the surplus variable. Another situation is we have 3x1 again plus 2x2. However, now this time I have larger than 3. Okay, in this case, I would like to do this. This time I want to minus, for example, t1 and make it equals to 3. And I want to make sure t1 is positive or 0. So if you have an equation where the left hand side is larger than the right hand side, what you can do is on the left hand side you can minus a surplus variable which must be positive or 0. Now you may have a question. Can we do this? Do what? Can we rewrite this as just swap the equation from left to right, and then can we do this? Have a plus s1 or s2 on the left hand side. Can we do this? Oh, and then when we plus s2 on the left hand side, this becomes a equal sign, right? So in this case, I should call this s as a slack variable. Can we do that? And we want to make sure s2 is positive or 0. If you do that, you will realize basically it's the same as surplus variable, right? When you reorganize them, it's the same set for the same purpose. So how about this? Can we try some other things? Can we do this? Can we no, I cannot think of something else. No. So basically, yeah. This is how you can make inequality constraints, rewrite them into equality ones. Okay? So when you introduce slack variables or surplus variables, the number of variables increases. Okay, so that's That's an issue. Number of variables increases. However, with this introduction of additional variables, you can use the method that we are going to introduce today, linear programming. Okay, good. Now, get back to linear programming. In this general format, actually we didn't mention whether this problem is linear or nonlinear. So in general, any function could be nonlinear. So what if you have nonlinear problems? Can you use linear programming? Yes, you can. So for nonlinear problems, what you can do is you can use first order Taylor expansion to approximate the function. So basically, you linearize nonlinear equations. So in this case, if I have a, let me make a drawing. If I have a design space, for example, x1 and x2, and for example, my object function could be linear. So for example, when I draw something like this is just to show you how the contour of the objective function look like, and the arrow is representing the descent direction. So this is the contour of f, and this is showing you descent direction. So if I move toward the arrow direction, function value drops. And let's say I have, for example, one nonlinear constraint like this. So for example, this is like a g1 of x must be smaller than 0. So for example, in this case, the iteration process may be helping me to move toward this position until I find the minimum within the safety region. And however, for linear programming, it cannot handle a nonlinear function like this. So let's say you have an initial guess right there. What you can do is to make linear approximations of the nonlinear function at your initial guess. So what you may get at the end could be an approximation of the function. So let's say the approximation could look like this. It may not be exactly correct, but slightly close to how the function look like. So this could be the first order Taylor expansion using your initial guess as expansion point. Then your objective function was originally linear, and now you have a approximated constraint which is linear. Then you can use linear programming. So at the end, you could be finding your solution, for example, somewhere here. Then you can perform linear approximation again in the second round, and you will have a more accurate approximation of the constraint when you are closer to the solution. So sometimes we do this sequentially. So there is an approach, so-called a sequential linear programming. What does sequential linear programming do? What it will do at the beginning is to perform linearization and then perform linear programming. And usually what you will do is to check convergency. If not, it will perform linearization again. If yes, optimal. So the usual procedure of sequential linear programming is like this. You will linearize your entire problem at the beginning, perform linear programming to get a better solution. Then you check whether it's converged. If not, do it again, linearize again. So you keep on doing this sequentially until the whole process converged. Okay, so today what we are going to learn is this part, how to do linear programming. So I'm not going to spend too much time on this entire process. I will mainly focus on linear programming. In the future, when you try to solve a nonlinear problem, this is one approach. You can linearize it and use what I teach you today to solve for a better solution. Then check convergency. If not yet, linearize again, LP. Check convergency. Keep on doing this sequentially until everything converged. Okay? Good. Now, let's get back to linear programming. So once you have a completely linearized problem, your objective function could be looking like this, minimizing c1x1 plus c2x2 plus c3x3 subject to a11x1 plus a12x2 plus a13x3 equals to b1 a21x1 plus a22x2 plus a23x3, where all the x are positive or 0 and all the b, let me make sure I'm using exact. Actually, let me extend this to a general form. We can have n of them. So I should have. I'm sorry, I can move around in iPad. If you are writing on papers, then you will hate me. Okay, so uh, let's call this J. And let's call this BI. Okay, so J from 1 to N, and I from 1 to M. Okay? So usually, so we have M equality constraints here, and we have N variables, including all the slack or surplus variables, if you have any. We just rename them as X. So totally we have N of them. We have N variables. We have M constraints. So there are several situations. If N equals to M, then basically you can solve for the solutions without optimization, because you have M equations and N unknowns. So there should exist, can solve for solution directly, can solve for solution directly by this. Right? If I call all the constraints as capital A dot X equals to B, and because the number of constraints equals to number of unknowns, then you can solve it. You don't even need optimization. So this is not the case we are looking for. In another case is where you have N larger than M. So you have no, smaller than, sorry. You have more constraints than your number of variables. So usually we call this overly constrained. And if it's overly constrained, sometimes it's hard to find solutions. You may not be able to find solutions. May not be able to find solutions. Okay? So in the other case, which is N that is larger than M, so this is called the under constraint. In this case, you can use optimization. To find a solution. So usually we can handle under constrained problems. You have more variables than number of equality constraints. So we won't talk about the above two scenarios, because for optimization those two are unusual, which means in the future if you try to solve a real problem where you face this kind of issue, then you need to think about, are you truly does the optimal solution truly exist? Okay, so the usual case is that you are under constraint. Okay, let's see. One thing that is very important, that is this fact and this fact. For linear programming, we need to rewrite the problem into certain form, so all the b's are positive. In some cases, you may have b equals to negative, where b is a negative value. If you see that, you can multiply the whole equation by -1, so the coefficient on the right hand side are positive. Linear programming solves this problem with a required format. If you don't follow the required format, it doesn't guarantee you finding the right solution. Okay, and also in the entire optimization process of linear programming, your x has to be positive. So what if your problem has variables that is within negative values? You can move your coordinate system. So let's say if I have a design problem, let's say x1 could be -2 from -2 to 5. What can we do? We can define y equals to x1 -2 or +2. So basically, let me do this. A +2. So in this case, I can do +2 for the entire equation. So I will have x1 +2. I can do this, right? I shift the coordinate. So at the end, I have this new variable. So for linear programming, I need my variables to be positive all the time. So this part satisfy the general formulation, and the right hand side, this part will be a part of the inequality constraint. So this one I can convert this whole thing into y plus a slack variable equals to 7, and slack variable is positive. So at the end, if I have this at the beginning, I end up with y plus s1 equals to 0, and also s1 positive, y positive. And all these on the right hand side satisfy the general format. The one on the left doesn't satisfy the general format yet. Okay? So if I define a new variable y, you may have a question. Then how can we get x at the end? Once you complete solving it, you know y equals to x plus 2. So x1 will be y minus 2 at the end. Once you get optimal y, you will know what is optimal x. Optimal s will be optimal y minus 2. So at the end, at the end, when you have optimal y, your optimal x1 star equals to optimal y minus 2. So you can get x1, optimal x1 at the end of the entire process. But in order to use the linear programming solution procedure, you have to rewrite the problem into this form. Otherwise, linear programming doesn't work. Okay? Now, that's it. Okay, so for the general format, I kind of apply the matrix form already, but I'm going to write down the matrix form for this general format. So we need this matrix form. So the matrix form looks like this. Okay, so to compare, you can see C vector basically is C1 to C, a vector of C1 to Cn. A matrix is the huge matrix that contains A11, A12 until Amn. B vector contains B1 to Bn. Okay? So I can kind of write down the size of them to remind you what they are. This is n by 1, right? We have a C1 to Cn, right? N by 1. B vector is m by 1. X is n by 1. A is, let me see, m by n. Okay? Just to remind you what they are, I write down the size of them next to it, so you will know what it is. Okay, so what we need to do later on is to kind of play with the matrix. So when we have matrix forms, actually we can write them into shapes of matrices. So let me make a drawing like this. Okay, so what is that? This is basically C transpose. This is X. In order to have C dot X, you need to transpose C and perform matrix multiplication. And this is like a horizontal vector times a vertical vector. I'm just plotting out the shape of the vectors. Okay, subject to I may have similar shape but wider. And here I should have exactly same size. Copy, paste. This should be my B. This would be my A matrix, right? So if I draw the length of the matrices on the side of it, this is basically the height of 1. This is like a width of n. This is like n right here. Here's 1 here. Right? And this guy is n by n. This guy is n by 1, and this guy is this is 1. This is n by 1, right? If you plot out the size of it, it looks like this. So what we are going to do is to make a cut into a certain format for derivation purpose. So we made a cut right here, and the size right here is m. So the size right here would be n minus m. Okay? And when we do that, maybe I would move this whole thing toward right a little bit so I can draw the size. Sorry. I can draw the size. This is m. So this is n by m. Right? So what I'm going to, once I make this cut, I'm going to name the cut in a certain way. I'm gonna call this guy A, B. I'm gonna call this guy A, N. I will tell you why. And over here, I'm going to call this guy B, XB. And I'm gonna call this guy XN. Okay? Similarly, I'm making a cut right here. Size of M. So here I should have size of n minus m. In this case, this would be my CB. This is my CN. And of course, this is a horizontal vector. So actually, this part is a transposed one. So what does B and N represent? B represent basic. N represent non-basic. To perform linear programming, we need to separate the matrix into two groups. One group belongs to the basic ones. The other group belongs to the non-basic ones. From here, you can tell if the number of n and m are the same, we cannot make this cut. In the other case, if the number m is larger than n, we cannot make this cut. We can only cut the matrix in this way when n is larger than m. Okay? That's why earlier we told you we can only solve for n larger than m. Okay? So we can make this cut. You won't be able to know what's going on. Why do we do this? But you will see later on. Okay, now we cut them in this way. Okay, that's fine. Okay, so we can now do one thing. We can have, for the constraint, we can now perform, we can rewrite them into a equation in this way. Basically, it's AB dot XB plus AN dot XN equals to B, right? If we are able to separate them in this form, we can write them down. This is exactly how it looked like in equation form when you write them down. So over here, we can get what XB is. It's gonna be B minus AN dot XN. Over here in the front, I have this AB inverse. I can derive this XB. Okay? And we can actually plug in to our objective function. We can plug in to our objective function. So when we do that, our objective function was C dot X or C transpose X, right? And we know earlier, over here I can cut it into half as well. This is the size right here is M, size here is N minus M, and this is X basic, X non-basic, right? So we know this could be written as C basic transpose X basic plus C non-basic transpose X non-basic. We can rewrite our objective function in this way. So I'm going to plug in my XB, what I just got earlier. So let me do that. CB transpose. Here I have AB inverse B minus AB inverse AN here XN plus CN transpose XN. Double check. CB AB inverse B AB inverse and XN. Yes, I'm just plugging in. I'm using this and plug in here, replacing that guy. Now I can rearrange the whole thing to expand all the terms. So I should have CB transpose AB inverse BB and just B, CB transpose AB inverse AN XN plus CN transpose XN. Okay. Now we found two terms that has the coefficient in front of xn. So let's put them together. So here I have CB transpose AB inverse B. Here I'm gonna use plus, so I will have CN transpose minus CB transpose AB inverse AN in front of XN. Okay? So what is this? It's a linear function. All these are just numbers. All these are numbers. C are numbers, A are numbers, B are numbers. So it's like some numbers right here, some numbers times a variable x. It's a linear function. Of course, it should be linear because originally we started with a linear problem. We just rewrite the linear objective function into certain format. And why do we only focus on x must be positive or 0? Right here, we know if we want to solve this problem using linear programming, we can only handle all the x be positive or 0. In this case, these doesn't change. It's not doesn't change. These are just numbers. So these are just numbers, or I should say scalar. No, numbers. Because it's a value. Yeah. So it's like a scalar based on how you cut A into half, into two groups, right? Because it depends on how you cut, how you decide the basic ones and the non-basic ones. If I cut my A matrix in a different way, the coefficients right here will be different. But they are just scalars. But over here, also, it's at the end it's a vector. Depends on how you cut A into two groups as well. But it's a vector. So how can we reduce the value of f? One way is to try to find the try to find a proper way to cut matrix A. So this part is negative. If this purple part is negative, then I can definitely make my function value lower because it's multiplying to x. X is positive. So if the coefficient is negative, then I should be able to reduce the objective function. So it seems like the way I separate A into two groups will affect how the objective function change its value. So we are looking for certain way to cut A into two groups so this part of the coefficients is negative. Because if it's negative, I can reduce the function value. Okay? So, now I'm going to introduce a procedure of doing linear programming by a real problem. And you may find this procedure a little weird, but it will use what I introduced right here. So we will jump into a real problem and then let's see how we solve it. So this is a real problem. Minimizing and those message will be used. Okay? So from here, you can already tell in this particular problem, we cannot directly solve it because we have inequality constraints. We need to rewrite it into a certain form. So this can be will be solvable by linear programming. Okay. So now, in order to solve it, we will introduce slack variables. I can copy whole thing. It makes my life easier. Sorry. Okay, now I'm introducing slack variables. Here I'm gonna have x3, it's a slack variable. Here I have x4, and here I have x5. They are slack variables, different ones, and x3 applied to the first constraint, x4 applied to the second one, x5 applied to the third one. Which means I will have 0 times x3 in the objective function. So it doesn't do anything to objective function. The objective function remains the same, but the you just have you enlarge your design space by adding 3 more variables. However, they don't contribute to the objective function. They only being added to the constraints, so the constraints are equality constraints, becoming equality constraints. Now I can rewrite this whole thing into the matrix form. Basically, we have this. Okay. So earlier I didn't tell you when we choose basic and non-basic, what's the trick? When we choose the basic ones, let me see. we want the non-basic ones to be 0. Okay, so here's a key idea of linear programming. We want the non-basic variables to be 0. Okay, so whenever we choose two variables to become non-basic, they will be assigned to be 0. Okay, so over here what we are going to start with is like this. We're going to say, okay, these three, consider them as basic, and these two, they are non-basic. In order to make the following derivation shorter, I'm going to use capital B to represent basic, capital N to represent non-basic. Okay? So if I cut the A matrix in this way, I can easily determine what's my x3, x4, and x5 at this point. Why? When I do this, this means I'm doing this. I am assigning x1 as 0, x2 as 0, and x3, x4, x5 being unknown. And from here, multiplying here, I can directly tell x3 equals to 2, x4 equals to 7, x5 equals to 3, right? This is the trick of making the initial guess of linear programming. So in this particular case, basically you start with x1 equals to 0 and x2 equals to 0. That's the trick. Okay? Does this trick always work? I can tell you sometimes it doesn't work. So linear programming sometimes cannot, it's not that powerful. Sometimes it just cannot handle certain type of problems. We don't talk about that kind of problems at this point. I'm gonna finish this problem, and in the next lecture, if we have time, I will tell you more. But that's just believe the procedure for now. Okay, so if I treat the last 3 columns as basic, then my first 2 columns are non-basic. And what I'm gonna do right now is to check the purple coefficient, the coefficient in purple. These. I'm gonna check this. So I'm gonna copy it here, paste it here. I'm checking this. Okay? So how do we do it? You just monitor what is Cn. In this case, for the first time, I'm writing it down. These 2 would be my Cn because non-basic. These 3 would be my Cb. These matrix would be my AB, and this matrix would be my AN. So basically just put them here. Cn transpose. Oh, I forgot about the transpose here. So this is basically -1, -2 minus 0, 0, 0. AB is this guy, and inverse times AN. AN is this guy. So at the end you will see it's -1 and -2. So what you are going to do next is to choose the most negative one. Here. This is the most negative one. What do you mean by one? Most negative coefficient. Of what? We can go back to the original derivation. This purple term represents the coefficient in front of the non-basic variables. What are the non-basic variables? At this point, the non-basic variables are x1 and x2. This is representing x1. This is representing x2. Right? Because we chose the first two columns of A as non-basic. So when we get a vector -1 and -2, they are coefficients in front of x1 and x2 in the objective function. So we are going to choose x2 because at this point x2 has the most negative coefficient in front of it. But x2 right now is 0. So if I start to add some number to x2, basically change the position of x2. If I add x2 by 1, if x2 is 1, the objective function will be -2. The larger x2 is, the smaller my function value is. So of course I want my x2 to be larger. So my objective function will be decreased, will be reduced. However, whenever I add a number to my x2, every time I need to satisfy my constraint. So the trick of linear programming is like this. We're always picking the coefficient, picking the variable that has the most negative coefficient. We are starting to add value to it. When we add value, meanwhile we need to check how other variables is going to change its value. So whenever x2 increases, all the rest of the variables will be changing its value at the same time, while satisfying all the constraints, until we can no longer add value to x2. We will move on to next iteration. So that's the trick. Let me write down the trick. So we want to add value to x2 because x2 now has the most negative coefficient in f of x. Then while adding value to x2, we want to satisfy all constraints simultaneously. We will keep adding value to x2 until we can no longer doing so, then we move on to next iteration. Okay, so this is basically what we are doing. So how do we now already decide to add value to x2. So what does it mean by adding value to x2? Basically, you want x2 to become a basic variable. So you want x2 to be a basic variable. So whenever we have a new basic variable, we need to pick up one basic variable and choose it as non-basic. So next step, whatever I'm writing here, how to achieve this, we need to pick up one variable and convert that one to non-basic. So in this case, we have currently my x1 and x2, they are non-basic, and my x3, x4, x5, they are basic. So I chose this one and I want to change it to basic. So one of the basics need to become non-basic. So the next step is to determine which one to become non-basic. When x2 is transferred from non-basic to basic, it won't be 0. When one of the basic becomes non-basic, that one becomes 0. So what linear programming is doing is constantly choosing what is the basic one, what is the non-basic ones. Okay? So how to do it? We are going to do some kind of check. So the way to check it is to follow the general equation here. So copy it and paste it. So we since we know this, so what we are doing right here is to actually, that means not using this one. Let me use the other one. Use this one. These are my basic variables. And from here you can tell the basic variables are functions of non-basic variables. Okay. So we can rewrite this as the following form. Here plus AB inverse B. Sorry. Plus AB inverse AN XN equals to AB inverse B. Okay, we can do that. So this is how A basic ones are related to the non-basic ones. And we're going to call this guy A hat. Oh no, A hat. It is a matrix. And we are going to call this guy B hat. It's a vector. So I guess I don't need this at the bottom. Okay. When we do this, let's check the dimension of it. So B vector xb would be having the same size of your constraint. In this case, we have 3 constraints. So xb is actually m by 1. AB is a square matrix in the size, in the width of number of your constraints. So this is actually m by m. Okay? B is m by 1. AN basically is AN is right here. This guy is AN. AN would be m by n minus m. So this is m by n minus m. Okay? Xn would be n minus m by 1. Okay? So we can check the dimension at the bottom as well. Here, the same thing, m by 1. This guy is m by m. This guy is an is m by n minus m. So from here you can tell at the end this is m by n minus m. So AB inverse is m by m. B is m by 1. So this would be m by 1. So knowing its size can help you to prevent making mistakes. Okay? In our case, we have n equals to 5, m equals to 3, right? So in our case, this is 3 by 1. This is basically 3 by 2. This is 3 by 1. Okay, so we can actually write them down. What are our xb at this point? x3, x4, and x5. Plus some matrix which is 3 by 2 times xn. xn is my x1 and x2 equals to some vector which is 3 by 1. Okay? So since we are focusing on x2, we want to add value to x2. So we are only focusing on x2. So what would be the coefficient for x2? This column. So in fact, we don't even care about x1. We only care about x2. x2 right now was 0. We want to start, we want to add values to x2. So we only, in this equation, we only care about what is multiplying x2. So this column basically is your A matrix, and you can say it's A let me see what was the index I used. It was I, is it? I equals to m to m, right? Let me see. Yes, okay. So I should tell you here, this is I equals to 1, right? This is I equals to 2. Yeah, that's fine. 3 equations. So this would be B1. This guy is your B2. This guy is your B3. And over here, I can say this is J equals to 1 and J equals to 2. So over here, they are A1 and 2. And this one will be A2 and 2. This one is A3 and 2. Okay, so basically they are A, I, and J's. On the right hand side, they are B, I's. Now we're going to do something called the ratio test. Ratio test. What does ratio test do? Ratio test performs BI over AIJ. Okay? We are going to do that. So in this case, before we perform the ratio test, we need to determine what are those coefficients. So this is the equation we are going to use later on for ratio test. Let me write down here. These are these, right? And we're going to perform ratio test in this way. But before we do those, we need to compute. We need to compute this and this. We need to know everything about A hat and B hat. So let's try to compute A, B inverse AN. This is my A hat. And B hat is my A. Okay? So my A basic right now is the identity matrix 1 1 1, right? So in the first iteration, it's always easy. My B is 273. My AN is this guy. AN is this guy. The 3 by 2 matrix. Okay? So let me just copy them to here. Oh, 1. -2, -1, 1, 1, 2, 0. Okay. Okay. So at the end, I would have exact same equation. Okay. And since I'm choosing the second column, so what I care the most would be these 3 numbers. And I'm now performing so-called the ratio test. So the ratio test gives me the B's over the A's, 1, 2, 0. So what I have at the end is 2, 3.5, and infinity. Okay? This is so-called the ratio test. And what do we do over here? We are going to choose the smallest positive one. We're going to do that. And when we do that, basically this guy, 2 was chosen. So when we do that, what does 2 represent? 2 represent the first row. So basically the 3 basic variables at this point. This is representing x3, this is representing x4, this is representing x5. So since we are choosing the smallest positive one, so x3 is chosen. And this one is to be selected as non-basic. Basic or yes, non-basic. So you may question, what's going on? Why this ratio test? Why are we doing this? Let me help you understand what's going on. These 3 are actually 3 linear functions. We can actually plot out those 3 linear functions. So the 3 linear functions look like this. They are x3, x4, and x5. And they are like coefficients 1, 2, and 0 in front of x2 equals to 2, 7, 3. We don't even care x1 anymore. This is what's happening. And if you draw the linear functions like this is x2, and basically they are like x2 equals to 3 linear equations. So it's gonna be like negative x3, negative x4. Sorry, I should do this. Negative x3, but 1 over 1, 1 over 2, 1 over 0, plus 2 over 1, plus 7 over 2, plus 3 over 0. So what we checked was the constant right here. What we checked was the constant right here. So there are actually 3 linear functions. Originally, this was originally 0 at the beginning. Okay? And if you draw those 3 functions, at the beginning, one of it was 2, the other one was 3.5, and the other one was infinity. No. Sorry. When x2 equals to 0, x3 was 2. And x4 was 7. and x5 was 3. So when x2 was 0, the values of x3, 4, and 5 are shown like this. So actually, I should draw this in a different way. I should write the function in a different way. Sorry. Delete. I should draw x3 equals to negative x2 plus 2. Yeah. x4 equals to negative 2x2 plus 7. So in fact, x5 remains 3 when you have increment of x2. So this line is this equation. Then the other one, this is increasing by 2, so it's like this. Down to here, this is 3.5. This is actually this equation. The other one is by negative 1, so it's like this. Over here is negative 2. So this is this line. Okay? So what happened was, I wish to increase the value of x2. When I increase it, x3 drops, x5 remains the same, x4 drops. I can increase x2 up to, this is positive 2. I can only increase x2 up to value of 2. So x3 becomes 0. And I can no longer increase x2 because x3 will become negative. In linear programming, all the variables needs to be positive of 0. That's why x3 was chosen. So what we're doing right here actually is this. We are changing values of our non-basic variables, and this was non-basic and was 0. We will increase x2 to positive 2. So x3 reduces to 0. So what happened to x3? x3 was basic, now become non-basic because it's becoming 0. Okay, so what we're doing right here, at the beginning, we chose one variable which has the most negative coefficient, and we wish that one to have value because it was 0. If we have some value to that variable x2, the objective function value drops because it has most negative coefficient. But when we do that, we are basically doing this. We are trying to increase the value of x2. But all the other variables are tightly related to x2. When you change x2, all the other variables has to change simultaneously. So we can only increase x2 up to certain level, so you can no longer increase x2. That's why at the end, x2 becomes value of 2, x3 becomes value of 0, and That's it. That's it for this iteration. What we can do next is to repeat the process again and see if we can improve it. Okay, so to sum up, we were having this. Now we know x3 will become non-basic. Okay, so that's the conclusion of first iteration. So what's next? In the next iteration, we will do something like this. So this is already next iteration. What do? We will remove all these selections. We will reselect who are basic, who are non-basic. But exact same problem. So at this point, x1 remains non-basic, x2 becomes basic, x3 is non-basic, x4 and 5 are basic. So the selection become a little weird. It's non-basic, basic, non-basic, basic, basic. Okay, so these columns are representing x1, x2, x3, x4, and x5. Okay, and we're going to repeat what happened earlier. So we are going to check. So now this is second time where we can speed up. We are checking this guy. Check this guy. Okay. What will be my Cn? Negative 1 and 0. Okay. What is my Cb? Negative 2, 0, 0. If you don't know what's going on, this is my Cn. I use purple. Cb, I use red. Okay? Multiplying AB inverse, AB will be where is my AB? I use yellow. This is my AB. Okay? So where is my AN? The rest. The one without color. Okay, so calculate this. And it's gonna take some time, so I already know the answer. It's negative 5 and 2. Okay? You can do it at home, but I already have it. So now I'm choosing the most negative one. And what does these two represent? These two coefficients represent the non-basic variables. So this is x1, this is x2. So basically my x1 needs to change. So the x1 needs to become basic. Okay, now we are going to do ratio test. When we do ratio test, we are computing these. Computing ratio test. So what's my AB inverse? It's right here. My B is 273. My AN is this guy. So I have the result already. I have the result. No, I don't. In my notes, I didn't finish. Okay, so let me ask MATLAB to tell me. Okay, I can only okay, so since we are choosing the first one as most negative, so we only care about the first column. And now we do ratio test. Ratio test basically 2, 3, 3 over negative 2, 3, and 1. So I have negative 1, 1, and 3. We choose the, oh, sorry. Okay, so I got it from MATLAB. We only, the red circle represent the most negative. This is the coefficient for the first column. The first column represents the coefficient in front of the variable you chose, like what you did earlier here. Okay, so now I am doing ratio tests like this. The yellow ones are here, over the purple ones are here. And remember, we are choosing the smallest positive one. And these are representing our current basic variables. Our current basics are x2, x4, and x5. Here, basics, right? So this tells us x4 needs to become non-basic. This iteration finishes. Move on to the next iteration. So once you know how to do it, it's not hard. You just repeat this. So let's try one more iteration. You are just confused by what's going on. How come this works? Well, if you know, then you don't need to be here. So first one become basic, second one remains the same, third one remains the same, fourth one become non-basic. So this is the new selection after what happened. So we are going to do this again. So I'm speeding up because my meeting is waiting for me. So Cn would be 0, 0 minus Cb would be this guy, AB inverse a n MATLAB Okay, so this tells me there's still some value that is negative. So this guy is chosen. This first guy was chosen. That is representing the first non-basic, which is x3. It's going to become basic. Okay, so next, do these. Do these, and I can copy this thing, copy, paste. MATLAB. I have to do it quickly, sorry. I will copy it so later on you will have it. Give me a second. Okay, get back to here. Okay, this is the result of MATLAB. Since we chose the first column, so this will be used, and we are going to do the ratio test. Obviously, only the last one is positive, so that one is chosen. So the last one is x5, becomes non-basic. Okay, do it again. Another iteration, and then this time the x3 is b, x4 n, x5 n. Okay, I hope that's the final iteration. So you need to do this, copy, paste it here, do it very quickly. Non-basic 0 0 minus -1 -2 0. Okay, I need a matrix here. The basic ones, oops. MATLAB. Okay. Okay, good. The result is 1 and 2. What does that mean? When the result is 1 and 2, that means in the objective function, in front of the non-basic coefficients, non-basic variables, the coefficients are positive. If I increase the values of them, the objective function increases. It doesn't improve our optimization. So we should stop. We can no longer reduce f. When you see positive in each coefficient you got right here, that means you can no longer improve. So converged. So if it's converged, what's the solution? The solution can be shown here. We don't even care about the negative ones, the zero ones. So we don't care. We don't care. You can use inverse of the matrix on the left and pre-multiply on the right. Then you got all your x. So at the end, this is basically you don't care about the zero ones, right? So you can, at the end, you will get, by solving this, you can get the value of x1, x2, and x3. So remember earlier we introduced three slack variables. The x4 and x5 they are actually zero at the end. x3 will be some value positive, and we don't even care what that value is at the end. What we care about is x1 and x2. They are the original variables in the problem. Okay? So this is how you can get your optimal. So that's it for today. I'm sorry, I have to run to a meeting and go back and check the lecture video and see if you can follow exactly what I did. Next time, I will review this part and I will introduce a different method to solve the same problem. And I will try to use MATLAB to write a code. And then next weekend, we will have the take-home exam. We will, in the take-home exam, you will be doing this, linear programming, okay? That's it. See you. Bye-bye.